Hi, my name is Julia Silgi, and I am a data scientist and software engineer at RStudio. And today in this screencast, we are going to train and tune a random forest model to predict the price of IKEA furniture. What I am excited about in this screencast is showing how to use some functions from tidymodels to generate scaffolding for really getting started quickly for some of the most common kind of models that people use in their real world work.
All right, let's get started building a model for this data set of prices for IKEA furniture. So this is from a couple of weeks ago. This data set of from Tidy Tuesday of pieces of furniture that have been with information that has been scraped from IKEA's website. Here's all these delightful IKEA names, Raskog and Noraker and Henriksdal and whatnot. And we have information about the category, the price, and Saudi Rials, information about a little bit of a description, the designer, the depth, and whatnot. And what we're going to do in this screencast is we're going to build a model to predict the prices from other information like that category and size. And I'm going to show, I think, something I have not shown in one of my screencasts, which is how to use a package we have for generating some boilerplate code for setting up a tidymodels tuning and training a model, which is pretty convenient. Before we get started, let's just do a little bit of some exploratory data analysis so we can know what we can expect to be important. So let's for example look at the let's say that width, I think, and put price on the y-axis, and then let's see how those are distributed, like so. So we've got some things that are missing. Let's make these a little bit transparent, so because they're overplotted a lot. And then everything's also very bunched up. So let's put these on a log scale. And actually that price is also on a log scale, like this. There we go. I think that's better. I don't know, maybe the width. Should the width be on a log scale? Maybe not. That's a tough one. Maybe we will not put the width on a log scale. So it's like 0 to 100, but it's distributed pretty nicely there. We might just keep it that way. So that's width. But we've got width, height, and depth. So let's reshape this. So if we've got this row that is like just a row number, effectively, like an ID. So if we take that, the price, and then depth, let's see, how does it go? It goes depth, height, width. So depth to width. And then if we do pivot longer, we can reshape this. So we reshape depth to width, and let's make the names to, let's call it dim, like this. This will reshape this for us. Notice that for some of these options that we have, we don't have all 3 dimensions. So we have the depth is NA for some of these. We know the height and the depth. For some things, we don't have any of them. So that number 2 here, let's scroll up for it. What is it? It is it's expensive. so it's a set. It's a bar table and 4 stools, excuse me. So we don't have any dimensions for that. So we're missing some of these things. But if we do this, then we will, instead of width, it's going to be called value. And we can say, let's make it color equals that dimension thing. And let's make this false, and then let's do a little facet wrap by dimension, like so. Nice. Okay. Okay, so the depth is much smaller than the width. Let's do this scales equals free x, and let's take off that. All right. All right. So something is really tall. I think that's a mistake. Okay, so the width, that looks like the strongest relationship to me, but is there anything here with height or depth? I don't know. Not much, maybe a little bit with depth. We'll see. So we have this information about width, height, and depth, and here is how they are related with price. Width definitely has the strongest relationship here. So this is a little bit of some exploratory data analysis. You know, bigger things tend to be more expensive. Definitely, it seems like width has the maybe the most reliable measurements that have been scraped there. So let's build a data frame that we will use for modeling here. So we need price. Let's keep that IKEA. So let's keep that name, because I wonder if some of these, so let's see. The names are not unique. Name. So there's a lot of them, more than we would want to have in the model, but I wonder if some of them are more expensive than others. For example, are some of them like a more luxurious line than others, or like are some of them more expensive kind of furniture or whatnot? So we can see, is name important? Category, are beds more expensive than chairs? And then let's have those depth, height, and width. And let's make that price. Let's take the log of it, because we are going to, just like we have in this plot, we are going to, oh, did I? Yeah. So it is on a log scale here, and I think that's the right thing to do. Price is often log normal distributed. And let's, if it is a character, let's change it to a factor. So let's call this IKEA DF, like this. So this will be what we're going to use for our modeling. And now let's set up and get that ready. So that's just a tiny bit of exploratory data analysis. We could definitely do more and learn more. But in the interest of getting going, let's do so. So let's, the first step as we get going is to set up basically what's our experimental design, how we're going to split up our data. So we're going to do an initial split on IKEA. So let's stratify by price, the thing we are going to use as our outcome. That's what we're trying to predict. So this is going to be our training testing split. And then we are going to get our training data. We will get it out of the split. Our testing data that we can get out of the split, like so. So this will be our testing training split. So the testing data we will hold to the very end to get a final estimate of how our model will perform on new data. Now let's look at making some resamples for tuning our model or comparing models. So let's try cross validation fold. So we make our resample off our training data only. We can also do this. We can also do stratified resampling here. Let's call that IKEA folds. All right, so this is our resampling setup. Oh, you know what? I don't think this is going to be too small for evaluating. I don't like that. Let's try bootstraps. That's better. Let's do this. So we'll do bootstrap resamples. So whenever we tune or use resample data sets, the model will be evaluated or trained fit on this, and then evaluated or assessed on this. And so we have 25 bootstrap resamples. We could change that if we want, but that's the default, which usually works well. And okay, so now I'm going to show what I think I have not shown in one of these screencasts, and that is these functions from this use models package, which has a lot of different options. For basically scaffolding for setting up common types of models. So it has several functions in it for common types of models, like use XGBoost, use GLMNet, use Earth, for use KKNN for K nearest neighbors models. So let's do a ranger random forest model. So the first thing we say is, what do we want the formula? So what do we want to predict price from all our other predictors that we have. And then the data that we have, we put in our training data like this. So if I execute this, look at what it spits out for me. It spits out boilerplate code to get me started on best practices for training a ranger random forest. So I've got a recipe, a model specification for tuning a random forest, a workflow that puts those together, and then the actual tuning. Notice there's a couple of things that are required for me to add in here. It will not run. I have to, it just doesn't automatically go. I have to think about what I need to do here. So I have to put in my folds, add your resample object here, and then I have to decide how many things do I want to try? How many candidate points do I want to try? Let's say I want to try 11 here. So I can now run this. I can now run this right now. I'm also going to add a parallel backend here so that it can run on my computer a little faster by using my cores that I have. So I could run this right now. However, this is really just a starting point. And I actually know a few things about my training data, about my data that I would like to take care of. And so I can actually go in here and customize this a little bit. So it's in some situations, you don't have to do anything. And in some situations, you can go in here and start to add whatever you need for your particular data. So for example, we said, hey, those names, there's like 600 different levels, and that is too many, I believe. So I can do step other. If you want a reminder of what step other does, we can look here. It collapses categorical levels down. So I'm going to collapse name. While I'm at it, let's collapse category down, and let's yeah, so let's do that. The threshold for that, I think, is going to be a little high. Let's lower it. Let's make so this means I'm going to keep more levels than if I use the default here. This is a random forest, so it can deal with a lot of levels. So but not 600. I mean, it could, but it will, it's not gonna work very well. The other thing is, um, these are kind of messy, and I don't like it's got, it's got all kinds of spaces, all kinds of punctuation in it. So I can add from the text recipes package, I can add a function called text clean levels. And I'm going to clean the name and the category, variables, so that they are going to have, instead of spaces, instead of capital, all caps, or title case, they're going to be all lower caps, all lowercase, and snake case. It will turn them into snake case, which will be nicer for some of my output. And then notice I've got all these NAs. I could have way up here, like if I did IKEA df, if I did na.omit, but wow, look, that throws away so much of my data. So instead of doing that, I can impute the missing ones. So if I do step kn and impute, and here are the things I want to impute: height, depth, height, width, like that. So I can impute the missing values for depth, height, and width based on the other values. So this, this doesn't add any new information. It just fills in the information based on a k nearest neighbors model, so that I don't have to throw away all these values. Okay, so I used the use model scaffolding to get started. And then I filled in a few other things feature engineering steps that I knew that I needed. And now I can just start this whole thing and run it. So this is, use models is so nice as a way to get started with some very common models that with some sensible defaults, and then sometimes you don't have to do anything. It can, tell what you need to do by the kind of data that you have. And sometimes you need to use some of your knowledge you gained during exploratory data analysis to make some other changes, especially the feature engineering steps. So this model is going to now tune. So what's happening is, for the 25 Bootstrap resamples, it is trying the 11 different candidate models that have different values of mtry and min-n, and it is going to train on the the analysis set of each part of the Bootstrap resample, and then assess on the the little assessment part of the Bootstrap resample, and then it's going to compute performance metrics for each of these 11 candidate models with different values for mtry and min-n. So let's let this run, and I will pause my video, and then I'll return when it's done and we can see what we got. Okay, we're back. That actually took less time than I thought I did, which is great. So now we can explore the results of this model that we finished, this set of tuning results that we have. So we can look at some of the best performing models by looking at these tune results that we have. We can look at we can, for example, say, hey, what are the best results by RMSE? So we can see here, there's the best RMSE here. Our two tuning parameters, remember, our mtry and min-n. We can change that to the other main metric, the other default metric for regression. Regression problems that we have, and it looks like it's the same, no big shock there. We can make I can spell auto plot. There we go. So we can look at all of the results here and see how this worked. So it looks here, let's zoom in here a bit. So it looks like, yeah, so our MC being low is good, our score being high is good. So it looks like we want this low minimal node size here, which that is the minimal node side is min n, and then mtry is how many predictors do you take at every where it splits. And so this kind of looks, so this was not a regular grid, this was a space filling design for how do you try different values for these tuning parameters. So it looks kind of like if we had tried a space filling, a regular grid, it may have had a curvy shape like this maybe. So it looks like minimal node size should probably be low, and we would maybe want something kind of in this regime over here, kind of over here. It looks like lower is better over here for something kind of over here for the randomly selected predictors. So that is mtry, that's over 2. So we can go ahead and update, or finalize is the word. We can take our workflow and we can finalize it, finalize workflow with with the best object here. We could save this separately if we want. We can call that final random forest. So this is our final random forest. You know, this is a final workflow is what we could call this here. And so now instead of these being tune parameters, they are finalized. We know what they are. And now let's do something called, let's do our final fit. So let's call it last fit. So we will fit the finalized workflow, the finalized random forest workflow to our split, which has testing and training data. So we will say IKEA fit here. So this is the last fit. So what we do in this is what's going on here is we are fitting to the whole training data at one time and then evaluating on the testing data. So we can look at the metrics. Whoops. I'm just trying to scroll. Here we go. Let me make that so it's not at the bottom of the screen. So we will collect metrics from the IKEA fit and IKEA fit. So these are metrics computed on the test set. And so if we compare this to these are from these resamples. So this is RMSE. So we can see, you know, it's a little bit lower, but you know, let's see, this is, what's the standard error? Yeah, a little bit lower. So we can understand like how much do we expect it to change here. And then we can collect the predictions out of it, which is these are the predictions on the test set. This is how much of the data we held back from the test set. And we can make a, whoops, what am I doing? We can plot that. So we see the price on the x-axis is the real true price, the predicted price. This is for the test set. And let's put a diagonal line showing 1 to 1. And then let's put these on as points. Here. And that can help this plot look pretty good. Okay, so this is our results on the test set. So how well can we do predicting the price of IKEA furniture based on its the kind of furniture it is, the size that it is, and its name. So, you know, that's not great. And we do a worse job on the cheaper furniture than we do on the more expensive furniture. So there's, cheaper things that we predict to be more expensive than they are, which is interesting. All right. So, these results are nothing to be shocked and amazed by, but isn't that always the way? Isn't that always the way? Okay, so if you wanted to save this for you're like, hey, I need to make predictions on this later. The trained workflow is in this object. It's right here. And so we can, if we have data like, I don't know, something like this, we can predict on this object. And we can, keep predicting, and we'll get out a predicted price. So this object right here is one that you can save as a binary object and predict from later. And then the last thing that I typically like to do is some kind of exploration of feature importance. I like to use the VIP package for this. For a ranger model, we actually have to go back to the spec that we made. And okay, so this model has tuning parameters. So we're going to do a couple things. We're going to finalize the model with that those same parameters. I should have saved that. And then we have to change the engine. We keep it as Ranger, which is the same as what it is here. We set the engine, but we have to add a way to compute the importance. So we're going to use the permutation-based importance here, like just permuting how we do the predictors. So we have to make like a new model specification here. We have to do this for Ranger models. The reason we could put importance up here, but it makes it slower. And if we're doing 11 times 25 models, it's probably not worth it. It's probably just worth it to train the model one more time down here. And so what we do is we make a whole nother model, but it's probably worth it because so now we add this model because it's worth doing this and now we fit to the whole training set. And then we will pull out the fitted model like this, and then we pipe it to VIP to get the importance out. This will make a nice plot. And if we want to change how the plot looks, we can pass something to aesthetics. Like you can make it, somewhat transparent. You can change the fill. This is going to make a bar chart, a geom call. Okay, so why did we have to go back and do this again? It's because otherwise it's not calculating the importance. Okay, so width is the most important thing. Remember, that's the one that had that strongest relationship when we did our exploratory data analysis. Then depth and height. Category and name was the least important. So that thing that had all the delightful IKEA Scandinavian names was the least important of all of them.
All right, we did it. We used this Tidy Tuesday data on IKEA furniture and its prices to train a random forest model. We learned that the width was most important in the predictions. That's probably because it was most like the best quality data. It seems like there was a little bit of some issues with some of the data there. But most importantly, we learned how to use these use models functions to quickly generate scaffolding for common models like Ranger Random Forest. It's also available for, other kinds of models like k-nearest neighbors and regularized regression models from GlimNet or GLMNet, however you prefer to say that. And we can take that scaffolding and then build onto it with whatever, we know we need to do for, say, feature engineering because of what we have in our particular data. So I hope that was helpful, and I will see you next time.